On the 21st of January 1916, a large area of virgin bushland in the vicinity of Tomago near Newcastle, New South Wales was reserved for water supply purposes and invested in the Hunter District Water Board. The first recorded advocate of the exploitation was the then Chief Engineer of the Board, Mr. Joshua B. Henson, who advocated consideration of this source of supply in preference to the construction of the Chichester Dam and pipeline. Early in the 1920s, Mr. Henson again advocated the Tomago water supply as a source of supply to Newcastle. As a result of his recommendations, a trial pumping station was erected at Tomago in 1922, and it operated for 111 days, pumping 43 million gallons of groundwater. The results of the trial were the background of later investigations and ultimately justified the construction of numbers 1 and 2 field pumping stations, which had been previously recommended by an engineering experts committee of which the then Chief Engineer, Mr. J.M.C. Corlett, was a member. Following satisfactory results from these 2 field pumping stations, the Board adopted a further recommendation from Mr. Corlett for the construction of 2 additional field pumping stations. The 1939-40 drought had seriously depleted the storage at Chichester. The Second World War brought about a high industrial consumption of water. In 1940, the Board adopted my recommendation that a major water supply scheme be developed at Tomago. The Board's decision has been fully justified by the increased demands for water supply. The origin of the area and a description of the major works will now be narrated.
In remote geological times, there existed a great bay of the sea whose shore extended from Port Stephens to East Maitland and back to Merriweather. Into this bay there entered 4 rivers, now known as the Hunter, the Patterson, the Williams, and the Karua. The rivers were laden with silt and gradually filled the bay with their deposits. At the same time, the Hunter River pushed its mouth further to the east, capturing the Patterson and the Williams rivers in the process. Finally, it discharged into the ocean between Merriweather and Port Stephens. Tilligerry Creek is the site of an old river bed. Over the bottom of this bay, vast quantities of mud were deposited so as to constitute a more or less level bottom, and this mud is now the floor of the present sand beds. Off the New South Wales coast, there is a fairly strong ocean current setting from north to south. As it travels down the coast, it carries with it large quantities of sand, which it frequently piles up behind any headland that juts into the sea. In a similar fashion, this ocean current piled up the vast deposit of sand which now constitutes the Tomago Sandbeds in the shelter behind the headlands of Port Stephens. The prevailing winds also played their part and blew inland some of the sand piled up by the ocean current. Fresh rainwater falling on the sea sands during many centuries washed out the salt and left the sand very clean. The impervious mud bottom holds the water and allows it to accumulate in the sand so that a great dome of water exists stored in the sand, the highest point in this dome being about 23 feet above sea level. The surplus water percolates to the sea and river, pushing the salt water before it. The average depth of the sand beds is 60 feet. The ground surface of the Tomago sand beds area is covered by gum trees of various kinds and low-lying scrub. The water supply works are located 10 miles from Newcastle, and the water is stored underground in the sand in localities almost free from habitation and industry. The Aborigines appreciated the area as a source of water, for the Aboriginal name Tomago means land of sweet water. This artificial basin, aptly named the Blue Lagoon, was created by the exploiters of the sand. It gives a ready indication of the extraordinary storage capacity of the sand beds, and the water level is its own evidence of the abundance of water immediately below the surface. The groundwater territory extends from the Hunter River on the south to Port Stephens on the north, the Pacific Ocean on the east, and to Raymond Terrace on the west. Of this territory, the board draws water from about 50 square miles. The investigatory work carried out prior to, as well as during the construction of the water supply works, involved the sinking of trial holes by means of auger and sand pump or sludger. The system is a simple one, consisting of boring a hole into the sand by means of an auger to ascertain the physical characteristics of the sand and of the water contained in it. The work of investigation necessitated the sinking of trial holes like this at points distributed over the 50 square miles and was a hand process. The method followed is demonstrated in these scenes made in the area during the progress of the work. A high standard of efficiency was shown by the field crew, and the undertaking in all stages was carried out with remarkable speed. When sinking the trial holes, and the permanent wells later, the drought conditions of the time were advantageous by reducing the natural flow of water into the holes. The free flow of water, however, was still abundant enough to necessitate the use of pumps to keep it under control during operations. The design of the major scheme embraced the building of 20 miles of roads, 20 miles of telephone lines, 24 miles of power lines, and 34 miles of pipeline ranging from 12-inch to 37.5-inch diameters. In view of the magnitude of the undertaking, it was remarkable that the initial scheme, commenced in 1937, could have been completed in 1941, making a water supply of 25 million gallons a day available to the city of Newcastle. The material requirements were naturally considerable. The construction of access roads necessitated the supply of over 20,000 cubic yards of gravel. The 900 drop pipes at tube wells and their connections to suction pipelines necessitated the use of 8 miles of 4-inch galvanized piping. In all, approximately 50,000 tons of materials, including pipes, road gravel, cement, concrete, aggregate, etc., were carted to the job. The board's engineers and contractors made extensive use of modern mechanized methods in carrying out the work. A Barber Green trenching machine was employed on smaller pipelines, whilst mechanical bucket excavators were used on the larger pipelines. Mobile cranes up to 10 tons capacity laid pipes in position in the trenches. Most of the bulk excavation at the spraying basin was done by tractor scoop and bulldozer. The delivery pipelines and the suction lines converge upon 15 field pumping stations, such as this one, and in each are 2 pumps with a capacity of 1 and 2 million gallons a day, respectively. In sinking wells, a casing with a serrated edge is lowered from a portable sinking frame 50 feet high. The water supply scheme required the construction of 900 wells in series of 60 at each pumping station. The 15-inch casing was suspended from the frame, and water from the surrounding area supplied the hydraulic pressure which enabled the casing to be sunk in the water-bearing sand to a depth of 44 feet. A portable pump was standard equipment to provide pressure water drawn from the sand to sink the tube well casing. The serrated edge of the casing cuts any hard sand as it's lowered from the frame, and the water creates a quicksand which facilitates penetration into the ground. As the casing is lowered, it is turned from side to side manually, and this action, enabling the teeth to cut while the natural water softens the sand, permits rapid work. Under the most favorable conditions, the sinking of the casing occupied 30 minutes. In this work, as in the sinking of the trial holes, the lower water table level, due to the prevailing drought, was advantageous to the engineers, though in spite of the drought, water was still present in considerable quantity. The excess water was controlled by pumps. When the casing had reached the required depth of 44 feet, a brass slotted well point, 4 inches in diameter and 5 feet long, containing almost 3,000 slots, was prepared and fixed to the end of a drop pipe. The well point, after being thus attached, is surrounded by a mesh bag or sock, and this in turn is filled with pea-sized river gravel. The gravel, descending with and round the slotted well point, prevents sand from being drawn in through the slots when the water passes from the surrounding sand. The cast iron cap on the casing was removed in readiness to take the drop pipe of the well. The lead weights prevent the casing from rising out of the sand as a result of the water press within the casing. The pre-packed well point and drop pipe was then lowered into the casing. As it descended, gravel of a finer gauge, about the size of rice, was packed round the end of the pipe. 900 such wells as this were sunk during the work, and the procedure in each case was identical. The depth reached by the well point was checked by the measuring rod, which protrudes from the casing, and the addition of fine gravel was repeated until a major portion of the pipe's length was surrounded by this material to assist the inflow of water. After the well was sunk, the removal of the casing followed. The measuring stick enables the crew to see that there is no runaway of the gravel. If this occurred,
the measuring stick would fall.
On its arrival at the basin, the water is sprayed to effect the total removal of the H2S and the partial removal of the CO2. This is done most effectively by the provision of 420 spray nozzles